Ja, jag är glad att se så många här. Välkomna till denna presskonferens där vi ska presentera årets Nobelpris i fysik. Welcome to this press conference where we will present this year's Nobel Prize in Physics. We will keep to the tradition and start in Swedish and then continue the presentation in English. And of course, you are free to pose questions in either language when we come to the question time. Ja, jag heter Staffan Normark och är ständig sekreterare här vid Kungliga Vetenskapsakademin. Och med mig som bisittare har jag två sakkunniga fysiker, professor Gunnar Ingelman, ordförande i klassen för fysik, som kan svara på frågor kring priset och som strax kommer att berätta lite mer. Och till vänster om mig har jag professor Olga Botner, ledamot i Nobelkommittén för fysik. Årets pris handlar om någonting oerhört litet som har en avgörande betydelse. Kungliga Vetenskapsakademin har beslutat utdela 2013 års Nobelpris i fysik till professor François Englert vid Université Libre de Bruxelles, Belgien, och professor Peter Higgs vid University of Edinburgh, Storbritannien. Akademins motivering lyder: för den teoretiska upptäckten av en mekanism som bidrar till förståelsen av massans ursprung hos subatomära partiklar och som nyligen genom upptäckten av den förutsagda fundamentala partikeln bekräftats av Atlas och CMS-experimenten vid CERNs accelerator LHC. This year's prize is about something very small that makes all the difference. The Royal Swedish Academy of Sciences has decided to award the 2013 Nobel Prize in Physics to Professor François Englert at Université Libre de Bruxelles, Belgique, and Professor Peter Higgs at University of Edinburgh, United Kingdom. And the Academy citation runs for the theoretical discovery of a mechanism that contributes to our understanding of the origin of mass of subatomic particles, and which recently was confirmed through the discovery of the predicted fundamental particle by the Atlas and CMS experiments at CERN's Large Hadron Collider. Professor Gunnar Ingelman will now give us a short summary in English, please.
This is a triumph, not only for Professor Englert and Professor Higgs, but for theoretical physics more generally, and actually the whole research field of elementary particle physics. It also illustrates the scientific method, namely to formulate theories based on mathematics in attempts to understand the laws of nature and testing them against experimental measurements. In 1964, François Englert, together with his now deceased colleague Robert Brout and Peter Higgs, proposed independently of each other the theory to solve the fundamental problem of how particles acquire mass. Their theory became a cornerstone of the standard model for elementary particle physics, which describes all matter as being built of a few kinds of basic matter particles, and all forces in nature as mediated by a few kinds of force particles. However, their theory required a totally new quantum field which should be manifested by a new and special kind of particle, the Higgs particle. This particle has now, at last, been observed last year by the Atlas and CMS collaborations or experiments at the International CERN laboratory outside Geneva in Switzerland.
Thank you, Professor Ingelman. And now I turn to Professor Olga Botner. Are you ready to give a more detailed presentation?
Yes, I do. Provided this works. Well, yes, so this brings me to the 4th of July 2012, which is a day that marks a new era in particle physics. And this is not only because François Englert and Peter Higgs met for the first time ever in front of a packed auditorium at CERN, but mainly because the ideas on mass of the fundamental particles had just been confirmed. But let us start by going 50 years back in time. In the autumn 1964, Anglaire, together with Robert Brout, who is now no longer with us, and Peter Higgs independently published 2 manuscripts explaining how certain particles can obtain mass. As you can see, the publication dates are only a few months apart. In the case of Higgs, October 19th. In the case of Anglaire and Brout, August 31. So both made a contribution to explaining the origin of mass, and these contributions cannot be distinguished. Now, what they did is central to the so-called standard model of particle physics. And let me try to explain what the standard model of particle physics is about by taking this example of a fly. So everything around us, and we ourselves, flowers, trees, stars, can be described in terms of a handful of constituents of matter and the forces acting between them. And so if you now look at the fly, it consists of molecules. Each molecule consists of atoms, and each atom has an atomic nucleus, and orbiting around the nucleus, we have electrons. Nuclei are not fundamental particles. The protons and neutrons have in turn fundamental constituents which we today believe are indivisible, and they are called quarks. Now, these fundamental matter particles interact by means of forces, and within quantum mechanics, we believe that these forces are mediated by quanta, by particles. And so we have the electromagnetic force mediated by photons, which are massless. We have the weak nuclear force mediated by massive particles, which are called W and Z. And we have the strong nuclear force mediated by massless gluons. Now, all is well and good, except that the theory behind the standard model would like all the mediator particles and all the matter particles to be massless. Now, here is the standard model of particle physics as we know it, with the matter constituents on the left-hand side, the quarks we've been talking about, the electrons, which you all know, part of the atoms, and the electrons' cousins, the green particles. On the right-hand side, we have the quanta, which mediate interactions between these particles, the Z and the W of the weak force, the photon, which we all know and love, and the gluons. And the theory would like all these particles to be massless. However, we all know they are not massless. I mean, we are not massless, unfortunately for some. So something must be there in the background to give these particles mass, and this is symbolized by this gray cloud in the background here with an H on top. So how can the world be so diverse? What is the origin of mass? Now, the problem is that to make the standard model work, we need theories which are basically symmetrical. But these symmetries forbid particles to have mass. If you try to put in mass by hand into the theories will collapse, and the standard model no longer works. So somehow the symmetries must be broken in such a way that keeps the good properties of the theory. Now, this is where the Mexican hat comes in. And I believe that everyone has seen this picture of the Mexican hat. Now, the Mexican hat symbolizes asymmetry. If you think in terms of a hat, you see a hat in front of you, and suppose you had the bag which sits on top in the center of the hat. To you, all the world looks symmetric. All directions are equivalent. However, if you slide down into the valley, then the world is no longer symmetric. There's obviously one direction in which it's easy to move, which is around the center, And there are directions in which it's difficult to move, and it's up and along the brim. And so now we have a situation which was symmetric to begin with, but which is no longer symmetric. Now this Mexican hat symbolizes, illustrates a piece of mathematics that Brout, Angler, and Higgs added into the theory to show that you could have a theory which was inherently symmetric, but where the ground state, the state of the lowest energy, did not display this symmetry. And this is what saved the Standard Model. Now, the theory made a concrete prediction, namely, 1, there should exist a new fundamental particle, and 2, all the other particles in nature, the matter particles and the quanta mediating forces, should gain mass through interactions with these particles. Which brings us back to the 4th of July, 2012. Appearing in front of a packed auditorium at CERN, the spokespersons of the experiments Atlas and CMS announced the observation of a new fundamental particles in proton-proton collisions at the Large Hadron Collider, which had properties consistent with the long sought-after Higgs particle. And you can imagine that the whole auditorium exploded in applause. Now here you see, again, Higgs and Angler waving to the auditorium after the announcement of the observation had been made. Now, what I'm going to show you is what the evidence for the existence of a new fundamental Higgs particle looks like. This is a little bit difficult, so I ask you to have a little bit of patience. So we have a diagram here showing on the horizontal axis the mass. Okay? Now, the Higgs particle cannot be seen directly. It can only be reconstructed from its decays, from traces it leaves in particle detectors. So from these traces, you can reconstruct the particle mass, but it is not clear it comes out exactly in one point. You can get many different masses. So on the horizontal axis, you have the reconstructed mass. On the vertical axis, you have the number of events found at each mass. There is another caveat, namely their background. There are processes mimicking the Higgs, which are not the Higgs particles. They are not the processes you're after. And they will be shown in blue in this diagram. So what you are going to look for is a red peak appearing in data against the blue background. And I'm going to show you how the data evolves with time. The black points will be data. And so look for the red peak and try to follow the time development. So here you see it comes up. As more and more data are collected, you see the blue background growing fast, but also the small red peak appearing. And this is the observation of the Higgs particle. Now, this is not the data they had in 2012. Now I'm showing you all the data we accumulated until the shutdown of LHC in the beginning of 2013. So I think I can stop this. This is what the data looks like. We see the red Higgs peak on the blue background. And so what we have here is the final piece in the puzzle, which is the Standard Model. This is, of course, not the final piece in the puzzle of the universe. There are still mysteries left. We don't know what the dark mass is. We don't know what the dark energy is. We don't know if Higgs is the only Higgs particle that exists or if there's more Higgs particles. So obviously, there are things to do for future generations of scientists. Thank you.
Thank you, Professor Bottner. We will now see if we can get hold of Professor Angler. I just talked to him a few minutes ago. Are you there with us, Professor Angler?
Yes, I am on the phone.
Oh, good day and congratulations. How do you feel right now?
Well, thank you very much. I feel very well, of course. I thought first I had to make a low festivity because I thought that I didn't see any announcement that I didn't have it, but now I'm very happy.
Yes. So I'm sitting here in the session hall at the Royal Swedish Academy of Sciences, and I have a large group of people from the media, international press. And are you ready to take some questions from the press, Professor Angler?
Yes, please. I will try to do what I can.
Okay. I have a question there.
Yes, hello, Professor Angler. My name is Maria Gunther Axelsson. I'm writing for the Swedish newspaper Dagens Nyheter, and you and I met this summer in Stockholm, if you remember. And congratulations to the prize.
Thank you very much. Yeah.
Yes, and I have a question for you.
Yes.
Now, when the standard model is complete, what is the biggest question?
I'm sorry, didn't hear well. What did you say?
Now that the standard model is complete,
yes.
Which, in your opinion, is the biggest question remaining to be solved in physics?
Well, there are a few big questions, right? First, the question which is still not solved is whether there is some broken supersymmetry which will manifest itself at energy which will not yet been reached. This is the critical point for what will happen. But of course, there are other problems, like which some of them may be directly related, some are other indirectly or maybe not related, which is the problem of dark matter is probably somehow, hopefully, related to particle physics. The problem of dark energy is a more tricky problem, which one way or another leads us to what is, in my opinion, the most and the fundamental problem which is not solved today, despite some progress, which is a problem of quantum gravity, or the quantization of gravity.
Okay. Do we have some other question?
Hi, so congratulations. My name is Konte Sinha from the Times of India. Very interestingly, the press release here starts with a line that says, "Here at last." Professor, how true is that?
I'm sorry, I didn't hear what you said.
No, I was saying that the press release here talks about, the first line in the release says, "Here at last." How true is that?
I'm afraid that maybe it's my phone or maybe it's my ear, but I don't understand exactly what you say.
We have you have a question? Yeah, you have it. Do you have a microphone?
Hello,
yeah.
Congratulations. My name is Joanna Rose. I work for a Swedish
Yes.
popular science magazine, Forskning och Framsteg. And I would like to ask you, in the late 60s, when you worked on the theory, did you ever think about the discovery of the Higgs boson?
Oh, yes, but the whole thing at that time, well, first, the late 60s is not really when the thing was done. It was the beginning of the 60s, and in 64. It was published after a lot of thought. At that time, we thought that we're going to solve this way the problem of short-range forces, which was completely unsolved at that time, and which obviously is related to the problem of the origin of mass. So the boson by itself is something that is the experimental test of the existence of the whole mechanism, and one had to wait. Certainly, we had to wait first before the theory itself was applied to something which is a standard model, which took some time. It took some time to first prove the consistency of our theory, which was up to the beginning of the 70s, and during the 70s, the standard model was built up. And only after that, could one look for a test? Because the standard model was wonderfully verified, except for the missing element, which was that boson, whose condensation is what gives the mass to particle and the short-range forces.
Okay, do we have another question, please?
Yes, hi, congratulations. This is Malin from the Associated Press. Of course, this was highly anticipated by all of us. But how did you feel when you found out about the award, and what are you planning to do with the prize money?
Well, the second question, I don't know. That's not my concern now. The first part of the question was what? About?
Just how does it feel to have won a Nobel Prize? I mean,
well, you may imagine that this is not very unpleasant, of course. I'm very, very happy to have that recognition of this extraordinary reward, and so I'm very happy of it. What can I say more?
okay, thank you.
Okay, I think we have a final question there.
Hello, this is David Landis with the local here in Stockholm. Congratulations, Professor Englert. A question about your co-winner. I'm wondering when you last spoke with Professor Higgs and what you plan to say to him when you see him next.
Well, I saw him, actually, the first time I saw him was in the 4th of July conference at CERN. We never met before. And but since then, we met, and we met in particularly at the EPS conference. And what I'm going to say to him, of course, I'm going to congratulate him, because I think he did a very important and excellent work.
Okay, thank you very much. And thank you very much. I think this was the last question from the press here. And thank you, Professor Englert. And once again, warm congratulations. And we look forward to see you in Stockholm in December for the Nobel Prize ceremony.
Yes.
Thank you.
Thank you.
Bye.
Bye.
So, are there now any questions about the physics prize and the research involved that you will pose to the panel here? We have a question there.
Jag kanske hinner först. Kan jag fråga på svenska? Ja, det här är ju ett stort teoretiskt genombrott, men det var ju också en väldigt stor experimentell succé, så att säga, en stor. Hur tänkte kommittén när man inte delade priset även till någon representant för experimenten?
Ska jag ta den frågan?
Kan du väl göra?
Ja, om frågan ställs till mig så kan jag försöka besvara den. Och det är förstås en fråga som är ganska uppenbart att ställa sig idag. Och det är så att det som kommittéerna har att utgå ifrån, det är först och främst är det Nobels testamente. Sen är det nomineringar. Och sen är det frågan om prisets tradition och prestige. Och allt detta tas in under diskussionerna i kommittéerna. Och sen så har vi alltså hamnat på ett prisförslag som är det som ni ser idag. Och det är klart att de interna diskussionerna inom kommittén är ingenting som vi kan avslöja för om 50 år.
Har vi någon annan fråga? Där.
Did you reach Professor Peter Higgs? Did you speak to him?
Actually, we tried quite hard to get hold of him, but of all the numbers we tried, he did not answer. So I hope he would know this by now. We are, of course, sending him an information right now by email, so he would have it also. But I have not been able to talk to him, unfortunately.
So is this why the announcement was delayed, or was there another reason? And why is
I
that?
can't comment on that, but I just tell you it's very important to stress that it is today that the Academy decides on the Nobel Prize. It's no other day. So this has happened just a few meters from this session hall. Okay, are there more questions? If not, I thank you very much for your attention, and we hope to see you back on Wednesday at 11:45 earliest. I think you have to look at that earliest for the announcement of the Nobel Prize in Chemistry 2013. Thank you very much.
Vi håller på, men vi är inte... Så? Precis, man ska ställa upp. Det är mycket man ska prata lite. Ja, vi håller på. Jag nämnde det. Jag kände en son till en vän till mig, Kowalski. Som är en kille. Eller han kanske...
Ja, han är inte så ung längre. Han är 40.
Olga Bottner, this year's prize must have been the most anticipated prize in the Nobel Prizes history. So why did we have to wait for more than an hour for the press conference?
Oh, you have to understand that the decision about the prize is taken on the very same day when it is announced. So there was a discussion, and there should be a discussion. Otherwise, if the prize is so anticipated, then no one in the academy even have to come to the decisive meeting. And today there were a number of people there, and there was a very good discussion, and we landed on this prize which was announced.
And these are two scientists, Angler and Higgs, who actually wrote the theory in the 60s, 1964. So they had to wait even longer for the prize. Why so?
Well, you know, there is a lot of theorists out there, and I'm an experimentalist myself, so you have to understand that my attitude towards theorists is, okay. So there are a lot of theories out there, there's a lot of theorists out there, but in the end, it's the interplay between experiment and theory which decides what nature has chosen as the grand scheme of things. And so it took 50 years for the prediction they made in 1964 to turn out to come true. And the thing which makes the prize interesting right now, you're asking why 50 years, is because of this observation of a new particle at CERN with the properties expected by the theory. So this is why. Sometimes you have to wait 50 years, and sometimes the theory may turn out to not be true.
And this is this so-called Higgs particle.
This is a so-called Higgs particle.
Yeah. Many people have heard about it. Why was it so hard to get it, to discover it?
Well, there are several things. One thing is that the theory predicted that there ought to be a particle. It could tell us the properties of this particle, so how it interacted with other particles, with matter particles and force carrier particles, but it couldn't tell us what the mass of this particle was. And so we didn't know where to look. And so actually for the past 50 years, this particle has been looked for at every accelerator in existence. So it has been looked for at the ISR, it has been looked for at the SPS at CERN, at the Lab Collider at the Tevatron. And this was an ongoing hunt. So from other properties, one could try to narrow the range of mass, and one did so both at Lab and the Tevatron. So in the end, we knew more or less that if it existed, it had to be there. And then the LHC came in. It is the most powerful accelerator in existence, could produce enough energy to make this happen. And so we found the particle.
They got it. Why is this particle so important?
Well, the particle in itself is not as important as the theory which it represents. So the theory tells us why we exist, more or less. Because as I said in my talk, this is a philosophical question then again, but maybe it tells us why we don't float away like the photon. I mean, we all know that we are massive. We know that we consist of atoms, and the atoms have atomic nuclei, protons and electrons, and neutrons. This is what we consist of. But according to the theories which existed before the mechanism was proposed, all these particles ought to have been massless. And we know that unfortunately we are massive. Some are more massive than other people, but definitely not massless. So there was something wrong, and the theory proposed a solution. And this is why the theory is important, and the particles is important as a manifestation of this theory.
So all particles get their masses from the Higgs field, the Higgs theory. And where does this Higgs particle exist? Is it here around us, or where is it?
Well, I have to modify this a little bit. All particles that we consist of get mass from the Higgs particle. There are particles which do not seem to interact with the Higgs particle, namely the neutrinos. And so the standard model is not completely complete. It is probably only a low energy approximation of something larger, which also explains the mass of the neutrinos, which also explains the dark matter. So at the moment we don't know. But electrons and protons and neutrons, the quarks inside them, get mass by interacting with the Higgs. So one way of looking at it is to imagine that the Higgs field is something which pervades all the universe. It's everywhere. It's here in the room, it's out in the black space, it's everywhere. And so every particle which moves through this field, and it's forced to, will interact with the Higgs particles, and in that way gets mass.
All the time, now?
All the time now.
And we don't see it?
We don't, I mean, we are born like that, right? So we wouldn't feel the field.
But where does this field and the particle come from?
Well, this is something that we actually don't know. I mean, this must have happened in the Big Bang somehow, that this is how our universe is constructed, that there is this field. It is possible that this field was part of the inflation process, which blew up the universe from a very tiny size to what we have today. We also don't know that. We don't know if there's only one Higgs field or maybe there's more Higgs fields. So there are still mysteries to be solved.
If this Higgs particle is so crucial to the whole universe and the discovery was so hard to make, why didn't the people who made the discovery get the Nobel Prize?
Well, this is, as you know, it's a very difficult question for me to answer, because we are not at liberty to divulge the discussions which take place inside the Nobel Committee or inside, indeed, the Academy when the decision is made. But let me just tell you that the decision on the prize is based on primarily the will of Alfred Nobel, on the nominations which we receive this very year. And then we, of course, take into account the prestige and the tradition of the prize. Now, weighing all these things together, we came up with the proposal of this year's prize. And now for the rest of the internal discussion, we'll have to wait 50 years.
I see. Maybe maybe next year. You spoke to François Englert, one of the laureates, but not to Peter Higgs.
That's right.
Will you try to call him again?
Yes, we're going to try to call him later today.
Yes.
And actually, I think we left a message on his recorder that we have, not that the Academy that have been trying to call him, but the Stockholm has been trying to call him. And we hope that he will respond. But the rumor has it that he has gone into hiding for the rest of the week in anticipation that, since this prize was so anticipated, he knew that in either case, if he gets it, there will be a press storm. If he doesn't get it, there will also be a press storm. So it felt like it was better to go into hiding.
So
instead.
now we are in the middle of the storm.
Yes.
And the Higgs particle has been said to be the last piece of the standard model puzzle for elementary particle physics. Is particle physics over now? Is it finished?
Well, the standard model is complete. So far, so good. But as I already told you, there are still unsolved things. One is the neutrinos. They somehow don't fit completely into the standard model. They do have mass, but apparently they're not getting their mass through interactions with Higgs. There's also the question why the Higgs is so light. Maybe there are more Higgs particles. Maybe this is just one of them and there are more to be found. So today the belief is that the standard model is a low energy approximation of a more complete theory. And this more complete theory is what particle physics is after now. So there are various speculations. Supersymmetry may be a possible extension of the standard model. There are also people speaking of extra dimensions, so that our four-dimensional world is just what we perceive of a larger 10-dimensional world, and the other dimensions are just tiny rolled up and we don't see them. So there are many speculations out there, and like with the Higgs, experiment will eventually show which theory is the right one.
Thank you very much, Olga,
You're most welcome.
taking your time.
Well, welcome. Thank you.